Yappa da 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 da, yappa da 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 da, yappa da da da, yappa da 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 do. There's an old saying, if you don't like the weather, give it a few minutes. The underlying concept here is of change. When we look at organisms of a particular area, they are often adapted to the local conditions. For instance, in cold climates, you might find adaptations such as fur or small appendages which reduce heat loss. Some insects have compounds that act as antifreeze. In climates that are weather stressed, cacti have developed adaptations like fluting that help them to take advantage of sudden water events. The point of mentioning these adaptations is that they take energy to build and maintain, and according to the allocation principle, organisms can't be perfectly adapted to every situation. The combination of changing environment and the inability to be perfectly adapted means that organisms will oftentimes be in conditions that are suboptimal. When conditions are suboptimal, organisms usually have to expend more energy trying to mediate the situation. For example, in warm-blooded organisms, once the temperature exceeds the thermal neutral zone of which it is adapted, more energy has to be expended to maintain its temperature. So an organism, such as a bat, might burn energy shivering to keep warm. In a cold-blooded insect, like the tiger beetle, it will behaviorally spend time and energy sun-facing, seeking shade, and shuttling between habitats to maintain an optimal temperature. For all of these adaptations, there still is an optimal set of conditions for the organism. The better the match, the higher the organism's fitness, because it will be able to put a larger percentage of resources into reproduction and not into survival. Fitness is the relative contribution of an organism to the next generation. In general, it's easy to see why parents would invest time and resources in their offspring, because it increases the probability of the offspring living and contributing to the next generation. But why would an organism like these bees help each other to raise offspring that wasn't their own? Yappa da 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 da, yappa da 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 da, yappa da da da, yappa da 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 do. Another case of spending time and energy for offspring that are not yours are with western bluebirds. Males of the western bluebird are nest helpers and help to feed offspring that are not their own. However, they are more likely to help with nests that they are closely related to. But why, when it doesn't help them contribute any offspring to the next generation? The answer lies with their genes. According to Janice Dickinson in 1996 and 2004, male western bluebirds are more likely to help out with nests that they are more closely related to, although relatedness could not predict how much they helped, just whether or not they did. By helping out with other nests, western bluebirds may not be passing on more offspring, but they can increase the proportion of their genes that make it into the next generation, through their relatives' offspring. This indirect contribution to the next generation is captured in the value of inclusive fitness. Inclusive fitness is an organism's direct contribution of offspring to the next generation, plus the indirect contribution of genes from closely related individuals. With evolution, organisms that have a higher fitness will be more represented in the next generation. Inclusive fitness works the same way. So even though your traits may not help you reproduce, as long as it helps your family reproduce, they still may be selected for. Inclusive fitness helps to explain why prairie dogs might call out a warning cry for a predator. Even though it puts the collar at more risk, it may help protect the collar's relatives and their offspring, increasing the prairie dog's overall inclusive fitness. Usually the direct portion of fitness is stronger than the indirect, meaning that traits that help you to reproduce your own offspring have stronger selection than those that maximize indirect fitness from relatives. However, this is not always the case. With bees, it is actually more beneficial to help your siblings. This difference is based on haplodiploidy, a genetic system in which one sex has only one copy of genes and the other has two. In the case of the honeybee, males are haploid, meaning they only have one genetic copy, and females, which are workers and queens, have two. In this case, when a female mates with a male to produce workers, the male contributes half of the genetic code, but they only have one copy. So all workers have the same copy from the male, meaning that they are 100% identical from the male's genetic copy. The queen has two copies and can give either set. So sisters in this case would have 50% of the queen's genetic code in common between them. The combination of these two contributions means that sisters share 75% of their genes. This means they pass on more of their genes to the next generation than if they had their own offspring, because then they would only share 50%, one copy from them and one copy from their mate. Bees work together to forage, protect from predation and parasitism, and also to thermoregulate. Bees will set up a current in the hive by lining up and beating their wings and setting up a circulating air current. This is one method that they use for surviving in suboptimal conditions and increasing their fitness, even if it is their sister's kids and not theirs.
This has been a Paper Pushers production.